All right, it's my pleasure to introduce Andy Applebaum, who is the lead cybersecurity engineer at MITRE, and they are running AttackCon like next week, so we're really grateful to have him take a step back from a really busy schedule and join us here at CAMLIS. Some of the things you know Andy from is he's been a previous speaker at Black Hat USA, where he's done a lot of things like red team automation and reasoning under uncertainty. He received his PhD in computer science from UC Davis and is here to join us now today to talk about making Meterpreter an adversarial example. So let's welcome Andy. Thank you.
You guys hear me okay? I think that is a yes. All right, so my name is Andy Applebaum. I'm going to be talking about some work I did on trying to make Meterpreter into an adversarial example. Just a quick about me, I'm a researcher at MITRE. As Hiram mentioned, I'm part of the attack team. Out of curiosity, is anybody else going to AttackCon? We got a couple of people, so I see some overlap. I'm also one of the leads on the Caldera project, which is designed to kind of automate the adversary emulation project. I have a strong personal interest in attacks against AI, and so that's kind of what this project is. This is kind of a personal project I had on, hey, how do adversarial examples relate back to security? The big question is, can we use reinforcement learning to generate evasive versions of Meterpreter? It includes a survey, which is more of a just kind of bullet point list of a bunch of cool papers, a short experiment that I ran, and then some analysis of the experimental results. Just a disclaimer, this is a fun project outside of my comfort zone, so I'm hoping I'll address everything perfectly, but if I look confused if you ask me a question, that's why. So before there was adversarial examples, there was machine learning, and I apologize, I'm starting from the beginning, but machine learning is amazing. It's made so much, so many things kind of, all these hard problems are now within reach because of machine learning, and that of course includes security. There are tons of papers, tons of companies, tons of stuff in security has a machine learning story nowadays, or an AI story, whichever you want to call it. We're all here after all. So I think that this goes without saying. And so the question is machine learning a silver bullet? And of course the answer is no, machine learning is not a silver bullet. You can't just say I'm going to go throw a classifier or something and I'm done, everything's great, I don't need to do any actual work. In 2013, this was kind of really embodied in this nice paper where they said, any good classifier, it should have like robustness in its classifications. If you slightly perturb the model, you make small changes, you should still have the same object being recognized there. And they discovered that, well, that's not always true with neural networks. Effectively, they found that by applying very small targeted perturbations to input images that were originally well classified, you could cause the classifier to misclassify the resultant image file. And here's some examples. And the laser works too well. But on the left in that figure, you can see there's a school bus over there. You had a little bit of kind of that gray noise in the middle. And then the right, that's an ostrich. And to me, that's still a school bus, but into the classifier, that's now an ostrich. And this field, since that 2013 paper, it's grown extensively. In 2015, there were two good papers out there which proposed new ways to construct adversarial examples that were very kind of fast and efficient. FGSM is, I think, the first one. The other one was, I think, the Jacobian-based approach. But both of those kind of required full access to the model where you saw all the internals of the neural network and you were able to kind of optimize how you were constructing the adversarial example. Over time, a lot of other construction techniques have emerged, and there's lots of different variants of kind of that same idea. One of the cool things is in 2018, there was a nice paper, Practical Black Box Attacks Against Machine Learning. The idea was, all right, we're not going to actually know what the internals of the model are. We're not even going to necessarily know what the model is. We're going to treat it as a black box. We're going to take our samples, we're going to throw them against the classifier, and all we get back is a label. Is it A or B? And they found that even that was enough to kind of construct techniques to construct adversarial examples. So trying to hide the classifier, it's a good idea, but it's not enough. And then there's other papers out there looking at kind of some defensive approaches. I haven't looked too much into it, but in 2017 there was a good paper of different ways that you could bypass some of the proposed defenses. And so a lot of those papers really focused on kind of digital adversarial examples where everything was digitally looked at. But one of the questions is, well, does this actually transfer into the real world? And unfortunately, the answer is yes, it does transfer into the real world. It's a nice paper in 2016 where if you printed an adversarial example, you could still have it be adversarial to the classifier. It would still misclassify it, even though the printer was somewhat lossy. And then the two other good ones, showed that you can modify real-world objects to cause them to be misclassified. And the stop sign is the great example there, where you modify what the stop sign looks like, and all of a sudden, even in the real world, it looks like something else. And then another good paper in 2018 was they created a patch that you apply it next to any object, and all of a sudden it looks like a toaster. It's fun. I wish I had a toaster. So the big thing here, there's a lot of papers there, and there's more to come. But the big thing is that adversarials are not really a one-off problem, or adversarial examples are not a one-off problem. They're kind of a thing. We should be worried about them a little bit. The defenses are not always intuitive. I know there's been some progress there lately. Assuming the classifier is hidden, that's not enough to defend against them. Attacks against, and I didn't really mention this too much, but oftentimes attacks against one classifier will transfer to another classifier. Kind of the bottom line is, if we're using some kind of machine learning classifier, we need to at the very least consider adversarial examples. So I said all this, adversarial examples are kind of a big deal, and I apologize, it's a really bad pun. Because Will Ferrell is a big deal, Anchorman. Looks like a Cylon now. Sorry, I had to. They're kind of a big deal, but how do they actually relate to security? A lot of these papers are about images, and they aren't necessarily about security. So does all this stuff, does it transfer into the security domain? And the big reason why we would doubt that is that at a very fundamental level, security is a different domain than image recognition. There's lots of reasons why, but my favorite one to point out actually goes back to that comment about FGSM and feature space and things like that. Perturbations in security are not always easy to apply. Modifying a file often corrupts it, and there's this great figure here, and I don't know if you can see it in the back, but the idea is we have kind of these three different ways we can corrupt that 3 on the left. You can perturb it to change the true class so the 3 becomes a 7. You can perturb it so that it's, you have that random little bit of noise, so yeah, it's a 3, but it's still a 3, but there's just some noise in the background. Or the bottom one is the rubbish class, where I'm going to take that 3, I'm going to add some noise there, and now it's no longer even a number, right? It's something that doesn't make any sense at all. And that's important in security because if we change a bit in a file, well, it's going to be different. It might not work anymore. So the question is, how well does the concept of adversarial examples transfer over? And the answer is, well, reasonably well. There's been a decent amount of research looking at this problem. Most of it focuses on the question of, malicious file classification, trying to kind of get a classifier to say, all right, this file is malicious, but I'm going to perturb it a little bit, and now I think it's benign. And so there's been a decent amount of work there, and what's interesting is that it's ranged across different threat models. Some early work, I think it was 2016, focused on using a white box model, so they had full access to the classifier. They focused on Android malware, and they would only add features to avoid that rubbish class problem. And given full knowledge of the model, I think they used FGSM to compute the best theoretical perturbation and found the perturbation that was kind of closest to that in the theoretical space, and that was sufficient to bypass it. Another threat model is the gray box model. This is another really good paper, I think 2016 as well. Here they focused on PDFs. They perturbed the file, and then they actually detonated it to ensure that their perturbations were actually legitimate, avoiding that rubbish class thing. They had no knowledge of the internals of the model, but they could query the classifier with a generated sample and get back a confidence score, so how confident the classifier was. And there they used a genetic algorithm, and just given that confidence score, that was sufficient for them to generate the adversarial example. And then on the bottom there, the black box testing approach, they focus on PE files, but only working in feature space. They modify the features, they don't necessarily modify the files themselves. And they can query the classifier, and instead of getting a confidence score, they just get the label, malicious or benign, that's it. And they use a generative network to modify the files to make samples evasive, and that worked reasonably well. And then one other paper that I really want to highlight, because it's kind of one of the crux of the talk, is this one by Anderson from 2018 that David had actually mentioned, where they work with real PE files and they modify the binary to kind of add additional features, things like adding an uncalled function, manipulating section names, packing or unpacking, appending bytes, things like that. And they, again, have that black box model where they only get the label benign or malicious, but they use reinforcement learning to kind of construct the sample. The idea being I'm going to make a modification, then test the resultant file. Is it malicious? If so, reward the classifier. If not, keep going. And they tested and trained on different malware classes, random malware, ransomware, and two other families there. And they got kind of mixed results. The agents, I know it's tiny there, but the agents were not significantly better than random, but it scored pretty strongly on VirusTotal. Some interesting stuff. So, okay. Lots of papers have been written, but it would be really cool if we could do this at home. And that's where this talk shifts a little bit to talk more about experimenting with adversarial examples, the Meterpreter portion. So as part of that 2018 paper, Anderson et al. Released an OpenAI gym to actually kind of run the experiments that they had used. Basically, it allows you to train an agent by a series of game, where each game is against a specific malware sample. During the agent's turn, it can select one of the built-in PE modifications, and then they test the modified malware against the classifier. If it's classified as benign, you end the game and you give it a big reward, saying, okay, yeah, you won, you tricked me. Otherwise, you keep playing the game until you run out of turns. The game could be run either in the black box scenario, as in the paper, or in a not published gray box scenario. The black box is kind of what we've been talking about, but the gray box, what you'd get is after each modification, instead of just getting the label benign or malicious, you'd also get the confidence as well. And they include a built-in agent to learn the policy, as well as a classifier that used a gradient-boosted decision tree. And so this is great. This works awesome out of the box. And all you need to do to use it is bring your own malware. Now, unfortunately, I don't have lots of malware lying around. And so I thought, wouldn't it be cool if I could use Meterpreter, the default Metasploit implant for training and testing. And this seems something fun to use because it's relatively benign and easy to handle. And it's also well known and reasonably well detected. I think when I compiled it with no options, 49 out of 68 on VirusTotal were able to pull it. From a technical perspective, it has lots of useful features, and there's lots of reasons why tons of people use Meterpreter. We'll go into them. And so this kind of gave three big, interesting research questions, at least interesting to me. First is, will the reinforcement learning technique be effective on a single type of malware? If we're only looking at Meterpreter, and can we kind of better optimize what we're doing than doing something randomly? Number two, can we perturb the detector so severely as to make something like Meterpreter, which is like, yeah, you should detect this? Can we make that evasive? And then the third question, which is interesting, is how effective is the not reported in the paper gray agent? Intuitively, I would think that would work really well, but it's a fun question to ask. So one of the problems with this whole idea is, well, gym-malware needs a large sample size to start with. You can't just say, here's one copy of Meterpreter, go train on that. You need lots of data. And so the solution was to dynamically compile different versions of Meterpreter with msfvenom, where msfvenom is a command line tool, kind of comes by default in Kali, or at least it used to compile different implants or shells with a variety of parameters. So what payload you have, the format, do you want it a PE, do you want a PHP, HTML file, I think is an option too. What encoder you use, the number of iterations to apply the encoder, whether or not you want to add code to your results. You can kind of say, all right, I'm going to compile Meterpreter, but I'm going to throw Outlook in there as well, kind of attached to the PE file. The number of NOPs, and then a template where, and this is an interesting one, where you can use an existing executable as a template for how you want the output to be structured. And so using msfvenom, we were able to write a script to generate about 4,000 different Meterpreter variants. All had some kind of base settings with them, but we varied the encoder, the number of iteration, the number of NOPs, the code we wanted added in, and the template that we wanted it to follow. And that kind of, you do the combinatorics, and you get around 4,000 different combinations there. So a couple of notes before diving into the results. Some notes on settings. First, gym-malware used a detection threshold. 0.9 was the default. Basically what happens is a classifier returns a score, 0 if it's benign, 1 if it's malicious. detection threshold defines where that cutoff is. So 0.9 or above, that's malicious. All samples classified as benign before any mutations or perturbations, those are tossed out. The game length, by default, is 10. That means you're allowed to make 10 perturbations before you kind of give up. We tested 10 as well as 20. 20 took forever, but that's another story. And then the total number of mutations was the total number of training trials the agent could run before terminating. I only did 20,000 as opposed to 50,000 because I made the foolish decision to run this on a laptop. Don't do that. And then the training and test size, the ultimate training size was about 2,100 with 200 testing samples. And the reason for that is that 43% of the initial variants that we generated were actually classified as benign. They were under that 0.9 threshold. So the results were largely underwhelming. There was no significant difference between the agents. You can see there in that second column, when we did 10 trials, the random agent, the black box agent, the gray box agent, all of them, kind of about the same percent that they were able to make evasive. And even if you increased the game length, that didn't really matter at all. In fact, the black box agent did 2.7% worse than the random agent. So there really wasn't much of a difference between the agents or the game lengths. But what was further interesting was that the discovered variants were, well, uninteresting. We generated a decent amount of them, 600, 700, but their average score, so once they dropped below the threshold, was just barely below the threshold. The average score was 0.87. So the perturbations were modifying it in a very, very slight way. So when this happened, I saw these results and I was a little upset because I was really expecting to generate all these cool things and make Meterpreter evasive, and that didn't happen. And so kind of in the post-mortem, reflecting, the first thing that I realized is I should probably have managed my expectations a little bit better. The original paper did not claim that this always produced evasions, and if you look at table 2, effectively, like there wasn't a large discernible difference between the agent and the random decision. The paper really argues that they can use the discover variants to retrain, which they saw a positive benefit from, and some of the evasions also looked a little bit better to some of the AV vendors, and those are the virus total there. Still have some questions about the gray agent, because I was really expecting that to do well, but well, that's actually the next slide, where managing expectations is one thing, but our actions that we're doing, are the perturbations, are they actually helping us? And so what I did was I applied each modification to each variant 5 times, because some of the modifications have some randomness to them. You record the average confidence score for those 5. Don't chain any of the modifications, just one at a time. Then record the overall confidence change, summed overall variance for each of the modifications. And the big thing here is that for all of the changes, the modifications actually made the classifier more confident that the file was malicious. You can see the plus sign there is basically like, on average, using any one of these would make it more confident that it was malicious. It didn't help at all. It in fact made it worse. And this actually makes the fact that the gray agent wasn't effective, that makes a lot more sense now, because the gray agent needs some sort of like monotonic thing to key off of, and all it's being given is things that are making it worse. So of course it's not going to work that well. And so some potential explanations here are, first, the classifier could have been trained on already obfuscated files, so it was like honing in on the obfuscations to begin with. Meterpreter might already be sufficiently optimized, or number 3, these obfuscations might just be ineffective. Having said that, what was effective, and I realize that you guys probably can't read this, all the way in the back at least, but what was actually effective was how we compiled Meterpreter. What options we gave it were actually very important for figuring out whether or not it would be classified as benign or malicious. The first interesting thing is that using an encoder, that made it worse. It was easier to detect any of the Meterpreter variants that used an encoder by about 0.14 or so. All the encoders were about equal. There wasn't a difference. If you use an encoder, that was bad. That makes it more obvious. Iterations and NOPs didn't make a difference at all, always the same. Adding code, appending code to the end of the PE file, always bad. Don't do that. That never worked. I'm not really surprised that adding like Mimikatz at the end of Meterpreter made it more malicious, but it did. And then templates, this is the interesting one. Always using a template helped. Not using a template had an average score of 0.93 as opposed to any of the others that had a score of less. And the really interesting one was using Mimikatz as a template gave us the best result. For whatever reason, making Meterpreter look like Mimikatz makes Meterpreter harder to see. I can't tell you why. The one interesting thing which I didn't test because of a bug in my code that I didn't realize after running all of the painstakingly long experiments was Putty was supposed to be in here as well, and I think when I tested this with Putty just, had a score of like 0.2 or something like that. If you made it look like Putty, it was really like, no, you're not picking this up. So okay, so I'm getting close to time, might even be beyond time, but a couple of closing thoughts, kind of revisiting the big research questions we wanted to look at. Well, number one, will the reinforcement learning technique be effective here? And no, but we should manage the expectation there better. Two, can we perturb the detector so severely to make the malware, this known malware evasive? Not really. It was kind of compiled to be evasive as it was. And then finally, number three was how effective is gym-malware as gray box agent? And surprisingly, not very, at least not here, not with Meterpreter and these kind of contrived, experimental settings. Some takeaways to walk away with. Number one, understand the threat model you're considering and the prior work behind it. That's important. Analyze your data before running your experiments. If I would have done like, hey, look at these compilation things and how important they are, these charts were really easy to make, whereas running the full experiment took a couple of weeks. Doing that beforehand would have been very helpful, at least for me. Reading the source material is important when you're forming your hypotheses, and then there's lots of other little things that you could tweak here that I suspect would give you some other interesting results. And a couple of things for the future that if I ever had more time, I would love to do. Finishing this experiment, I want to look at how action space and the compilation options interact. So, are different perturbations, are they better with, if I'm including Mimikatz for whatever reason? Investigating the gray agent in more detail. I still feel like there's opportunity there. Maybe it was the experimental design, but intuitively, I would like to see that do better. And then the last one is, can we smartly optimize the generation of adversarial examples? Here I just kind of went through and brute forced all 4,000, ran through all the options with msfvenom, but if you imagine a larger search space, is there a way to do this more in a way that's more optimized, doing it before the fact as opposed to after the fact? This is really cool because if you do this, you can solve the problems with the rubbish class because you're compiling it and it's, if your compiler is good, then you're guaranteed to actually have it work. With that, I think I have like 5 minutes for questions.
Andy, thank you. We do have a few moments for questions. Sorry.
Thanks, that was a great talk. I'd like to hearten you a little bit by saying that I did that census where you test how much each perturbation will influence the score of the model. I did that on a very large data set, not just Meterpreter. Found the same thing, that the average effect is positive across a very large corpus of malware. The interesting detail is that it's not always positive for every sample. There's some combinations of modification plus original sample that is evasive, and I didn't have time to investigate why, but if you're looking for something to look at next, that would be a suggestion.
Yeah, that's what I think, I didn't have time to do this, is looking at how the action space and the compilation options. I would be curious to see if there's interplay there between the two.
And I just wanted to make one comment. Cool work. I love the idea of instead of focusing on a broad sort of samples, focus on a specific. I do want to point out that the original code, the reinforcement learning, that kind of the purpose of that is that you can train on samples and then present it a new sample it's never seen, and it tries to trick that sample out to evade. But in your case, if you're focusing on one sample, you could actually do like what Shu et al. Did, or David Evans, where they just essentially have a genetic algorithm that systematically tries to reduce that gray box score. You could probably get evade every last one of those samples. So that's an interesting, cool twist on focusing on a particular software platform and adding in those compile time options. That's awesome.
Thanks, that was an awesome talk. I have a really simple question, which is, did the templates and things like that affect file size at some extent, and did that have any correlation?
That's a good question. I didn't look into that enough. Anecdotally, not really too much, just because I kind of skipped this, I guess. But the files we were using as templates were like fgdump, netcat, mimicat, who is, and the only one that was relatively large was like PS exec. But, anecdotally, when I was looking at them, they were usually within the ballpark of each other.
Very interesting talk. So my question is, so you mentioned that in generating the adversarial examples to bypass the classifiers, you said you're mainly using reinforcement learning approach. So can you give us a little bit more details about that approach? Like you mentioned that the action space is actually just perturbations to the feature values.
Yeah. So
then how about the state space? That's one quick question. And another second question, very quick, is that I remember you also mentioned that using a genetic algorithm to generate adversarial examples. So are these the only two approaches you tried, or did you make a comparison with these two approaches or even more approaches?
So the second question first, not yet. I'd like to look into genetic algorithms, as Hiram mentioned. Like, I think that's a very interesting area, especially if you're focusing on like one corpus of malware. The first question about the state space, I am blanking.
I can answer that one, actually. The state space is essentially the Ember feature set. So the model that's baked into gym-malware is actually the precursor to Ember 2017 model. So it has the state space are features extracted from the PE file.
Thanks for the talk. Just a quick question. You mentioned that you did not changes together. I'm still not very clear on what the action space is, and if the action space is just a single perturbation, like adding a no-op at the end of the file. This isn't what RL is made to do. RL is for sequential decision making. So you want to learn what chain of actions.
So gym-malware did chain the actions for the actual experiments. This slide here is, I was curious like how effective each of these was on its own outside of the chaining concept, because the idea is like, I don't think the chain's going to be that effective if the individual components are all kind of like making it worse. Now, I might be wrong. Probably am wrong. David's looking at me. Oh. But it was one of those things where I'm trying to like double check that the reinforcement learning like actually has sufficient things to go with where the actions are helping, because this, if you're doing it as the one-off like this, that's suggesting to me the actions are not helping. They're actually making it worse. So chaining them probably isn't going to end up helping you. It might, but it will be a big lift there.
Did you discover that there are any interesting sequences of transformations when you were looking at chains, or did you not examine that?
No, I didn't get a chance to examine that one.
All right, let's thank our speaker one more time. Thank you.